All right, guys. Yesterday, we were discussing that if we have the sine function, okay, with the sine function, what goes right here? An angle, okay? And you get back a ratio that is opposite divided by hypotenuse, right? Okay, so when we talk about the inverse, the sine inverse, those things switch spots because of the relationship that we know from college algebra about how inverses relate to one another, okay? And that if a comma b is on one of the functions, then b comma a is on the inverse. So then this will be a ratio here, okay? And we discussed that, okay, if that's the case, then because the opposite side divided by hypotenuse if I'm in the first quadrant, the hypotenuse is always what in comparison to the opposite side? It's bigger. So this number can only be between, looking in the first quadrant, 0 to 1, right? Okay. But we also know that we could be down here, because there's only two options for where my y's could be. Okay? If my y were down here, my opposite side would be a negative divided by hypotenuse, so it'd be 0 to negative 1. Okay? So what we find out is that this input value can only be between negative 1 to 1. And because it's this image, my angles can only become from negative pi over 2 to pi over 2. Or negative 90 to positive 90 if we were to write it as degrees. Okay? When we talk about the cosine function, same idea. The cosine, still going to put an angle here. It's going to give you a ratio. Well, what's the ratio in cosine? What sides are they? Adjacent divided by hypotenuse, right? So in the cosine inverse, right down here, cosine inverse, that's going to be adjacent divided by hypotenuse. It's going to spit back an angle. But now with the cosine, okay, you're looking at the x values being the adjacent, so there's my hypotenuse, and then we'd be talking about maybe that distance right there. So that comparison with this being the adjacent divided by the hypotenuse, that distance, or that quotient would be between 0 and 1, right? If we go over here, that quotient will be, because this is going to be a negative now, that quotient of adjacent and hypotenuse is going to be between 0 and negative 1. So again, the input here is negative 1 to 1. The output's a little bit different. The output, okay, would be all of these angles here instead of all of these angles that were there. Does that make sense? So the output is going to be between 0 and 180, or in radians, 0 to pi. Okay. Does this make sense? We talked about it in chapter 5 a little bit. Let's talk about a relationship that becomes very, 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 very beneficial for us. I'm just going to draw, I think I drew this yesterday, but I think it's beneficial to talk about again. If this is a function f, and this is a function g, okay? And let's call this function, so this is f of x. Let's say it's x squared. This is g of x. Call it root x. Those two functions right now, based on what we know, are what to one another? They're inverses. So if I think the number we used yesterday was 7. Put 7 in, it squares it, spits out 49, correct? 49 now becomes the input here, square roots it, spits back 7, correct? Okay? You started with an x, you ran it through a composite function. So the way that we have this set up, the function that we ran it through first was f. So right now, really what we did collectively was that. We took the composite of g of f of x. Does that make sense? You plugged x in of 7, and you got 7 spit back, right? So what we're seeing there was that g of f of 7 gave you back 7. If I go g of f of 8, does it give me back 8? If I go g of f of 10, does it give me back 10? Right? Does that make sense, everybody? Okay. The idea there then is that if you take g of f of x, it spits back x. Okay. Now, if we do it the opposite direction, where this is g, and this is f. Okay, now if I plug in, let's just say, do an easy one, let's plug in 16. If I plug in 16, it will square root it, spit back 4, right? That 4 then runs through here and gets squared, and what's it spit back? 16, right? Okay, so that relation that we just determined is because we went through g first, that was f of g of x. That's what this image is displaying. Well, what we just realized then is that f of g of x, what does that spit back? X. These were the two conditions that had to be met if two functions were going to be inverses. Okay? If two functions are inverses, this is true. Okay? Does that make sense to everybody? Now, it is only true for where these inner functions are defined. So for this red one, f of x is defined everywhere. So there's no issues there. On this one, g of x is not defined everywhere, right? So if I plug in like -1, I can't do that anymore. Okay? So there's a restriction there that we have to keep in mind. And when we talk about the graph and the one-to-one nature of x squared and root of x, we'll talk about that in a moment. But that should segue us into understanding sine and cosine and their inverses. Okay? If we have, let's say, the sine function, and then the sine inverse nestled inside of it, okay, that's a composite function, right? Okay, what that is saying, let's say that sine of x is, let's call that our f of x, and let's say sine inverse of x is our g of x. We know by the way they're named, they're inverses, so this rule right here should apply. Okay, so what we've got then is this scenario here would be f of g of x. Does that make sense, everybody? Okay, so I should get x back, but I only get x back for the values in which the sine inverse is defined for. So what numbers am I allowed to put in that green set of parentheses there? So the sine inverse. Where is the sine inverse defined for on the x-axis? -1 to 1. The ratio of opposite divided by hypotenuse, that's the only thing that can go in there. Okay? So if I choose a number right there that is -1 to 1, what is going to happen is this cancellation rule right there. We call it a cancellation rule because basically what we're going to do is say if that sign cancels that and leaves you just that. Does that make sense? So if I go sine of sine inverse of, let's just say, 2/3, okay, I type that in to a calculator. Now I'm going to use the arc sine notation. That's still sine inverse. Okay. If I type in 2/3, Does it spit back 2/3? Yeah. And the reason for that is because that 2/3 is between -1 and 1. Let me ask you this. What is my calculator going to do with that? What's that number right there have to be? Between -1 and 1. That's the only because of that's the input values that you're allowed to use. It's like saying square root. The input values on a square root that I'm allowed to use are 0 to infinity. I can't use negatives, right? So the sine inverse, I can't use numbers to the right of 1 or to the left of -1. So what my calculator is going to say, or what it's going to know, is this is an undefined amount. Okay? Which means that it ultimately doesn't exist. So then there is absolutely no way that it's going to be able to take the sign of something that it doesn't know. Does that make sense? Okay? So if you type that in, you can see that it provides undefined. Okay? Anything outside 1, -1 will do that. If we flip the concept, so instead of we're going f of g of x, let's go g of f of x. Should still give me x. Okay? But we'll talk about when that happens. So I've got the sine inverse of sine of x. Okay? That will give me x. But what does that number have to be in order for us to be able to take the inverse? If I put a number in here, okay, let's say I put, this has to be an angle, right? That angle, we want it to be, because what is going to happen here, okay, is that we want a number right here that when I take the inverse out here, we get ultimately the inverse of something between -1 and 1. Does that make sense, everybody? I want this whole thing in parentheses here to evaluate between -1 and 1. Well, based off of what we have already talked about with the sine function, the only values that can happen with the way it's defined is that if we use -π/2 to +π/2. Does that make sense? Okay. And that is what is described, if you downloaded the notes, right here. Okay, a lot of stuff written over. Last class we did the same thing, but I wrote it in this area. Right here, it's saying that the sine of the sine inverse of x, okay? So if you think about it as like f of g of x is equal to x, but only where that innermost function is defined. The innermost function is defined between -1 and 1. If I reverse the roles and go sine inverse of sine of x is equal to x, only when that innermost function is defined from -π/2 to +π/2. Okay? Another way of thinking about that is think about the unit circle. The unit circle is made up of a bunch of triangles, correct? And those triangles were right triangles, correct? So if I'm looking at the right triangles, and I'm looking at basically when we use sine, cosine, we're only using those for the acute angles of a right triangle. Well, the acute angles of a right triangle can only, because it's a right triangle and 90 degrees is already being eaten up by the right angle, then that remaining set of acute angles are complementary, so the largest that one of those can be is ultimately 90 degrees. Does that make sense? It's actually like 89.99999. But because we could happen that in the top quadrants or the bottom quadrants, that's where we go from -π/2 to +π/2. But your acute angle, the theta, something like, so I draw our image here, that angle right there, theta, can only ever be between 0 and 90 degrees or 0 and -90 degrees. Does that make sense? Okay, because that's the way triangles are constructed. And the negative just tells us it's going in the opposite direction. Is that okay with everybody? Sam, do you have a question? So when we have, so basically I can only evaluate this. I can only do that evaluation. I can only get something spit back to us if this innermost function is defined, right? If that innermost function, when I evaluate it, it gives me a number, so that I can take the sine of that number. Well, the only thing that you're allowed to plug into the sum, because remember, that's got to be a ratio for the sine inverse, right? And the ratio is always opposite divided by hypotenuse. That number will always be between 0 and 1. But because the hypotenuse has to be the biggest value, right? But so if it was between 0 and 1, it would basically restrict us to the first quadrant. So we know we can move that direction as well. And now the y value would be negative. So the O value here would be negative. So then we have also 0 to negative 1, and that's why negative 1 to 1 are these values. Then those are the only values that can spit back. So once this number here gets evaluated, so if it's anywhere between negative 1 and 1, this will spit back ultimately an angle measurement for us. And then I can take the sine of an angle measurement that is between negative 90 and positive 90. That is just one perspective of looking at why these relationships are what they are. Let's look at a graphical approach to this. It starts to what? Repeat? Yes. That's the graphical thing that we're going to look at here. Okay? So let's do that real quick. Let's look at and I've got and you'll see maybe the purpose of this here in a little bit. I've got my y-axis now being the axis written in terms of my radians. And you'll see here in a little bit why. Mari? The best way that I can explain that is, I'm going to try to give you two explanations, I guess. When we look at opposite over hypotenuse, let's do it this way. That's a question that when I understand this, I can visualize this, but I can't articulate the best explanation using this approach. But I can with the graphical approach. Let's look at the graphical approach today. So let's look at sine of x first. That's the sine of x, right? So when we look at the graphical approach, we want to talk about that thing's inverse. When we look at that thing's inverse, we have to make sure of two things in order to get an inverse. First, it has to be a function, which means that it has to pass the vertical line test, which means that every x value has one and one y value, right? One and only one y value. Okay? Meaning that if I tell you guys to look at an x value of pi over 2, that pi over 2 is going to have a y value of 1. Does that make sense? If I tell you to look at pi over 6, you're going to say, okay, well, pi over 6, that y value is 1/2. You're going to know one and only one y value that goes with every x value that I ask you for. That's the definition of a function. Past the vertical line test, we know that was a function, right? What test does this fail, though? The horizontal line test, okay? And it fails the horizontal line test because if I ask you to give me the x values where y is some number, I'll just choose y to be 1 because it's the easier one here, I think. It's like, give me the x value that y is 1. Are some of you going to give me this x value right here, which would be pi over 2? Are some of you going to give me this x value over here, which would be 5 pi over 2? Would some of you give me this one, which would be negative 3 pi over 2? Okay? So there's a lot of different x values that can be given back where I tell you a specific y value. So that means this thing is not going to pass the horizontal line test, which means it's not 1-to-1. Okay? Let's draw a comparison back to something we've already done. If I give you this, give you that curve right there, does that pass the vertical line test? That's a function, right? X squared. Does it fail the horizontal line test? Yeah, so that thing did not have an inverse. because it has to pass the horizontal line test to be one-to-one, and only one-to-one functions have inverses. But we know there is something that undoes x squared. We've been using that with all the explanations already, right? What is the inverse of x squared? Square root of x, okay? But what kind of numbers are you not allowed to take square roots of? Negative numbers. And the reason we're not allowed to take square roots of negative numbers is because in order to make this thing one-to-one, we had to do this. We had to cut the negative x values off. We had to restrict the domain, right? So when I restrict the domain of x squared, now that's going to restrict the range of, sorry, if I restrict that domain, when I find its inverse, I'm going to restrict the things that I can put into radical x. Does that make sense? Okay. So that blue curve is now one-to-one. So is there a similar thing that maybe we could do with the sine function? Okay. Now understanding, let's go back to this real quick. We talked about earlier in college algebra why that thing, or what behavior happens that we can recognize that is going to ultimately lead to the rejection of the horizontal line test. And it's when the graph shows two behaviors. Would you guys agree the green graph is showing a decrease followed by an increase? But when it does those two things, it will always fail the horizontal line test because it's going to go back through y values that it already hit. So what we do is we restrict the domain to where the graph is strictly, we refer to it as strictly monotonic. Means it's doing one thing and only one thing. Okay, that's only increasing now, right? Well, if we look at this graph, right now we don't have that. We have increase and decrease all across the spectrum here. So what we want to do is we want to narrow our focus. We want to restrict our domain so that we get only increasing or only a decreasing portion of that graph. Okay, so there's a lot of different places you could do this, but when we do it somewhere else along the x-axis than where we are going to do it, what we would have to do is transform that thing to make it as simple as possible. So what we're trying to show you is the smallest interval in which this thing is only increasing, and try to keep it near 0, 0. So what I'm going to do here real quick, I'm going to just say x is less than a, and x is greater than b, and I don't know what b was, but that was wrong. X is greater than, let's put k in. There we go. And we're going to, let's open those all the way up to 5. Okay, so so I'm looking at my entire sine function. It goes from negative infinity to positive infinity. But then I take scissors and I chop it off where that black stuff starts. Okay? Still fail the horizontal line test, right? But do I fail it less times than I did previously? Yeah. Okay. Let's keep moving those black bars in towards one another. I'm going to fail less times, right? Move this one in. I fail the horizontal line test less times. Let's move them both to negative pi and positive pi. Okay. Would you guys agree that if I put in, let's go y equals m, create m, and I don't know if I'll be able to, there we go. I was afraid of that. I can't see where that toggle is for this. Nope. No. Can you see if I took that red line and started moving it up and down, I'm still going to fail the vertical line test, right? Or sorry, the horizontal line test, right? Okay. But in that first quadrant, I would only be intersecting twice, right? If I kept the y, if I looked at that y value and made it go through, that red line go through like a y value of 1/2, I'm only going to intersect that thing 2 times. So if I can see y equals 0.5, okay? So let's move this black region in past that point right there, correct? So now, when I do that, now that horizontal line test works, right? But if I were to move that to like 0.75, it's not going to work. It's going to still intersect there. But if I keep moving that in further and further, both sides, to maybe about right there, and this one to about right there, now can you see the sine curve only increasing? Okay, look at those numbers that I chose for K. 1.6. Is that pretty close to 1.57? Anybody remember what 1.57 was without? That's pi over 2. Okay. So what we find out is if I take the the sine function and I restrict it between pi over 2 and positive pi over 2 to give me that blue curve right there. And that blue curve is only increasing. So if it's only increasing, it's going to pass the vertical and horizontal line test, so it's going to have an inverse. Meaning, if it has an inverse, okay, there's a point on that blue curve right now, negative pi over 2, negative 1, right? That point A. There's a point 0, 0. There's a point pi over 2, comma 1, right? I'm just going to take those 3, but we could take all the other ones in there, negative pi over 6, negative 1/2, negative pi over 3, negative radical 3 over 2, positive pi over 6, 1/2, positive pi over 3, radical 3 over 2. And those are just coming off the unit circle. If I take those points, take A, which is at negative pi over 2, negative 1, and find its inverse, essentially. If I have A comma B, then I'm going to find B comma A, right? That's what I'm doing here. So this is negative pi over 2 comma negative 1, so I'm going to write it this way. And it gives me point D. Point B is going to be, we're going to invert point B, it's still point B. And then C is going to be 1 comma pi over 2, and I get that. So now, when I find and I connect those points and all those other ones that were in there that I've inverted, I'm going to get that purple curve. And now if I look at that purple curve, what are the x values? What are the domain values for the purple curve? Between negative 1 and 1, right? What are the y values? What are the outputs? Negative pi over 2 to pi over 2. And I think that's the best explanation of why the sine inverse only gives back negative 90 to positive 90 or negative pi over 2 to positive pi over 2. Does that make sense? Okay. That then leads us to down the road when we were trying to solve trigonometric equations, our calculator is going to give us one answer. But we know that from that one answer, we've got the unit circle idea, and we understand the periodic behavior of sine and cosine curves, that one answer from the calculator can be manipulated or adjusted to get multiple answers, okay, that the calculator isn't capable of giving us. All right, so that's the sine function of sine inverse. Okay, why does the cosine only go from 0 to 180? Why is the output 0 to pi essentially? Well, let's look at the cosine function. And think about this real quick. We've talked about the cosine function being the sine function shifted 90 degrees, right? Or the sine function shifted 90 degrees. Well, if I take my range of negative 90 to positive 90, and I shift it 90 degrees, does that give me now a distance or a set of angles between 0 and 180. That kind of makes sense. So I'm taking the first and fourth quadrants and rotating them back up, and they become the first and second quadrants. So that might be a way of thinking about it, but I like to think about using the graph here, using the same thing that we talked about previously. That fails the horizontal line test. Fails it everywhere, okay? Now we can't, if I go like x equal, we use the same restriction as before, okay? And I look just between negative pi over 2 and pi over 2 like we did for the sine function, that thing still fails, doesn't it? Okay? But didn't we said that it's a shift 90 degrees, or a shift pi over 2. Let's shift those asymptotes pi over 2 to the right. Okay? Now you could go pi over 2 to the left, but it's just easier or more logical to go to the right. And if I shift them pi over 2 units to the right, so that pi over 2 one would go out to pi. And now if I look in between those two asymptotes, I don't want to say asymptotes, look through those two x values, okay, created by those bars, is that graph only decreasing? All right, so let's just type it this way real quick. Let's go, if x is between 0 and pi, let's look at the cosine function. And it's that right there. Okay, so it's strictly decreasing. So using, obviously we got the point 0, 1. We got the point pi over 2, 0. We got the point pi negative 1. If I take A and invert it, so 0, 1 becomes 1, 0. Take B, so it's at pi over 2, 0, so it goes 0, pi over 2. And I take C, which is at pi negative 1, it comes negative 1 pi. I invert those points. It gives me these three blue points, right? F, E, and D. If I connect those and all the other points that I would have inverted in between them, it gives me that red curve. Okay, and again, what are inverses? Aren't they reflections across that line right there? And that looks like a valid reflection, right? But if let's hide this one. Let's get rid of that. There is your cosine inverse. And you see the x values now, or where that thing is defined, are between negative 1 and 1. And you see that the y values go from 0 to pi, or 0 to 180 in degrees. Does that make sense? Okay, so then these cancellations occur only, so remember what composite functions are. Composite, if that's the arc cosine, and this is the cosine, okay, if I ask you the question, okay, if I say, let's go cosine inverse of cosine, let me put the x-axis in terms of pi as well to make this a little bit easier to see. Okay, so if I ask you cosine inverse of cosine of, let's just say 3 pi over 2, okay, what you would do here is you go find innermost function, cosine of 3 pi over 2. So that's the input. I look right there, and what is the output that I get? What's the y value back that I get? It'd be 0, right? So now I go cosine inverse of 0. Well, does the cosine inverse, is that defined for 0? I'm going to go find the cosine inverse, which is the red curve, and look at the x value of 0, and doesn't it give me pi over 2 in that case? Does that make sense? Okay. Now we'll talk about why it didn't give me back directly 3 pi over 2 as it has in the past, maybe. Let's do this. Let's go to cosine inverse of cosine of pi. Cosine of pi. What's cosine of pi? Give me back a y value. Cosine of pi is -1, right? So give me back -1. So I go cosine, then this thing turns into -1. And now I ask, okay, well, what is the cosine inverse of -1? You know, look at an x value of -1 on the cosine. And what's the y value gives back? It'd be pi, right? There was a direct cancellation. You're left with just the pi. Okay? But if I asked you this question, what is the cosine of the cosine inverse of, like, let's say 3? 3 would be about right there, wouldn't it? Does that line of 3, does that ever intersect the red curve? So the red curve's not defined at 3, so you cannot do this. But I can if I go cosine inverse of, let's say, I'll just say 1/2. If I go find 1/2, so let's put the x-axis back in integer form. Wish they had a toggle switch that would allow me to do this a little bit easier. So 1/2. So I find 1/2 on the cosine inverse, and that's going to give me back pi over 3, right? So now the question would be, well, what does, so this thing goes to pi over 3, what is cosine of pi over 3? So now I'm going to go to the cosine and find pi over 3, which now the cosine of pi over 3 is going to be, well, let's put it back in so we judge this a little bit easier. Put it back into radians. Pi over 3 is going to be about right here, isn't it? Okay. And it's going to give, cosine of pi over 3 is going to give me back the 1/2. Okay. Does that kind of make sense? Okay. So that's why these cancellation rules only work for certain x values. Okay. Certain, right here, why is sine inverse of x equals x? Why is that only for x between -1 and 1? It's because I'm grabbing a value off of a function, and that function needs to be defined so I can get that value. Okay. But what's going to happen is that this is going to allow us to answer questions like these, which these are more fundamental, kind of simplistic questions initially. They're going to say, what is the sine inverse of 1/2? Okay, sine inverse of 1/2. Well, we can do that one of two ways. You can either you can have the unit circle directly in front of you. You can use your calculator. Calculator's only going to give it back in degrees, though. That would make sense to us if it was our calculator was in radians, we'd give the decimal version back. Or we're going to just go from memory. Okay. But using the unit circle approach, if I say sine inverse of 1/2, well, that 1/2 is a ratio, correct? That's the input of every inverse function. Okay, that is the input of every inverse function. So, if they're inputting 1/2, I'm going to go and say, okay, well, what angle, because that's what I want to get back, what angle has an out or a value of the y value that is 1/2? So I search around here, and I know it's a sine inverse, so I can only look at the green region, the first and fourth quadrants. And I see that it gives 1/2 back right there, right? So my answer to that would be 30 degrees or pi over 6. Okay? Now what stinks about this, let's write sine of 1/2 equals 30. So then the sine inverse of 30 should give me back what? Should give me back 1/2. Those, because the 30 is between -90 and +90, these things are going to switch spots, right? But on my, look at my unit circle. Is there another angle other than 30 that has a y value of 1/2? 150. Okay? So I could say sine inverse of 150. Okay? Now my calculator is going to probably balk at that. Okay? Actually, my calculator is going to be fine at this. Sine inverse of 150. My calculator should give me back 1/2. Okay? However, when I type in sine of 1/2, it's not going to give me like 30, 150. It's not going to give me both those answers. Does that make sense? Okay. So when we go through, this will be the last step of an equation in the next section. We will go to something that looks like this. We'll say we want maybe we get sine of x equals 1/2. Okay? Well, then the next thing that we're going to do to get this x out is we're going to take the sine inverse of this side, and there's going to be cancellation that happens. And when that cancellation happens, we're assuming that we're going between negative pi over pi over 2 and pi over 2. So those are the only results I'm going to get back. Take the sine inverse of this side, leaves me with x. Take the sine inverse of this side, leaves me with that, right? Then I can use the unit circle and say, oh, that's 30 degrees. But what we find out is that 150 is also another angle measurement that will satisfy the given condition because the sine curve repeats itself from negative infinity to positive infinity, right? So you're going to have more than one answer. We'll pick up with that tomorrow. Maybe. If not tomorrow, Monday. Plan tomorrow, quiz over the parent function, sine, cosine, tangent, cotangent, secant, cosecant. Probably take, well, I'll give you the whole period, 25 minutes to do that. Plan on at least the parent functions, how to plot the points for those parent functions. No calculator or anything like that.